is everybody? Surviving? Be careful if you say that during a pandemic. We do already have 2 kids between this class and the next class in quarantine because they were exposed. No one in the classes has it yet that I know of. So we are trying to zoom in and hopefully we can get it to work. Who'd like to start us off with a prayer? Thanks, Michael. Amen. Thank you. Okay, a few things before we get started. Any questions from the syllabus? Great. Okay. You're so confused you don't know what to ask. TAs really fast. Is the next online homework 2.1a? Can you check? All right, while he's looking that up, this is the homework that's due for next time, or that's assigned today. So this is kind of a crazy day because we're making the transition from doing stuff after class to doing stuff before class. Luckily, there's no online 1.3, okay? So you're going to read the section 1.3. It's a pretty short section. We're going to start 2.1. So you're going to read those sections. You're going to do the online homework on 2.1. And 2.1, chapter 2 starts systems of equations. It's something that a lot of you are really comfortable with, okay? So it's not going to be crazy. There's some videos on Learning Suite. Next to the videos, we're also putting slides, right? Do you have them up? So almost all the other teachers for linear algebra, they use the same set of slides. And they just walk through the slides for their lecture. I'm going to put the slides up so you guys have access to those too. And instead of watching the videos, if you want to just study the slides, then you can do that too. So the advantage of this, studying the slides, it kind of covers everything, but you might miss some of the depth. And the videos, they'll go more in depth on some problems, okay? And so on the online homework that is due before class, it will ask, did you read the sections and did you watch the video? If you studied the slides instead, you can say, yes, I watched the video. Okay, you're not lying if you do that. And can you guys hear me okay? Okay. And then the book homework for 1.2, we're going to talk about 1.2 today. You're going to do that, and you'll upload that to Gradescope. We hope. We're still working on Gradescope, so you have more information to come. Any questions on those? Yes.
Where do we find the videos?
The videos are on Learning Suite. Do you want to pull up Learning Suite? And she'll pull it up so we can show you exactly where those videos are and those slides. Great question. I meant to pull it up. Samuel.
So basically, we're reading 2 sections, doing online homework, and doing book homework, and watching video.
Yep, that's right. But after that, usually after class, you'll have a book homework, and before the next class, you'll read the section, watch the video, or look at the slides, and do the online homework. So you'll kind of finish up. Between 2 class periods, you'll finish up one, and you'll start the next. So here, and then Samuel. You bet. Can you pull up WebAssign too? Okay. Samuel, what was your question?
Isn't there WebAssign for 1.2 tomorrow night?
Oh, did I not get the online for 1.2 up?
Right now, you have to change it to the 1.1, 1.2, and 2.1 are due.
Yes. Dang. I hate to give you guys another assignment, but I really do. So yeah, I forgot about the online 1.2. So On the syllabus, it said the online 1.1 and the online 1.2 were due pretty quick. It said like by Wednesday at midnight, online 1.1 was due. By Friday, like tomorrow at midnight, 1.2 is due. We pushed those off, so they're really due by next Tuesday, okay? I knew people, well, already we have people that are just adding the class, so it was just easier and gives you guys a little bit more flexibility to get the homework done. So, okay. What do you have? Okay. Perfect. So here, go to student view. All right. So when we say online homework, this is what we mean. So you're in here, in WebAssign, you say, okay, the online homework for 1.1, you click on it, you do those problems, okay? The bookwork, do you want to go to Learning Suite? The bookwork problems, go to assignments, where is that? Go to home and then assignments. Oh yeah, we're here. There, if you click on, if you go to the scheduler assignments, you click on that, it tells you what the problems are from the book, but you have to go back to the online system to find the book to find those problems. Okay, sorry, I'm sorry, I should have been more clear about this. Samuel and then Bryn? Lauren, dang it. Okay.
So are we like taking a picture of our bookwork and like uploading it somewhere, or?
That's the plan. We're trying to get Gradescope, and yeah, you will upload it to a program called Gradescope, but we're still trying to get it all set up. So we will email you. These are all awesome questions. Lauren?
I see that there's 3 assignment homework assigned to you on September 8th. Is that right, or the date's wrong?
That is correct.
Okay.
But they're all due then because we just pushed the 1.1 and like 1.1, we moved back. You should have already done it, but we know people are going to be late, you know, with the adding and the dropping, and I pushed it off till then. Yeah, there's 2 due then because 1.2 you do after. We're in this between today and Tuesday. We're transitioning from doing some stuff after class to some stuff before class, so it's kind of an overloaded period. I apologize for that, but then it should all settle down after that. Luckily, the next content's pretty easy. So once we start chapter 2, a lot of you are going to be super comfortable with the first part of chapter 2. Yep.
I apologize if you already answered this, but on the grades on Learning Suite, it has like points assigned to homework 1.1, the written portion, but it also says like do not complete. And so,
Yeah, I made that decision a little late. They probably already put it in. Yeah, it was probably already in Gradebook, so yeah, we'll drop that. So don't worry about it. You won't get points for doing the online, I mean the book homework for 1.1. So, yes, Tiffany.
I will have written 1.2 due on Gradescope on Tuesday.
Yep.
And not 2.1.
And not 2.1. Yeah, because written's after today, written's always happen. Well, written's always happen afterwards. The online's supposed to happen before, but yes, someone else had their hand up.
Was it the 1.1 bookwork or online work that was assigned last period?
yes.
Both. Yeah. Yep. Okay. On the next semester when I do this, when I teach this again, we'll make that a lot more clear. Okay. Yep. Can you pull up the Zoom office hours? So under the content page on Learning Suite, there's a few things to the left. So one of them says Zoom links for office hours. So here, during their posted office hours, you can go to those Zoom links and they'll be there. I've been a little late the last couple days. No one's joined, but if I'm not there, I'm going to actually put my telephone number there, and then you can call in case I'm not on, or if I'm not hearing you and you're on or something like that. So also the videos and the lecture slides are on here. So Sam, that was to answer your question. So the video's up there. It says which ones are required for 1.2 and for the lecture slides. So there's the slides for the different sections.
But also, like, under each day, I have broken up into each section.
Oh, that's right. Oh, very nice. So all of the slides just for 1.1 are just right there. All the slides for 1.2. So from now on, like when we do 1.3, if there's any slides associated with 1.3, they'll be right there. Okay. All right. Okay. Do you want to pull up the slides? And if you want to post that. So if I'm talking about stuff you already know either from the videos or the reading that you've done, you can start working on a couple. These are problems from a midterm a semester or two ago. So you can start working on these, okay, to challenge yourself. But I'm going to start talking about dot products in general. We'll do some other stuff. So, okay, so dot products, like if you're dealing with packets, one natural question, packets of numbers or vectors, is how similar are these two vectors? Or how similar is this packet to this packet? Dot products to help us to answer that question. How similar are they? A dot product takes in two vectors, okay, and it spits out a scalar, okay, a real number, some number on the real line, on the real number line. We introduce it, we call it a dot product because it has this, I should make that bigger, a kind of a bold dot in here. It can be a little confusing because sometimes they'll do a smaller dot and they just mean scalar multiplication, and the big dot means dot product, okay? The dot product, if you've got two vectors, like so, what's the dot product of those? You multiply the corresponding entries, and then you add all of those products up. Okay, so this is like the procedure of doing a dot product. How does it help us to know how similar they are? Well, in the dot product, if they're similar, you get a large positive number. If they're unrelated, you get 0. And if they're negatively related, trying to write bigger. Sorry, I noticed I was getting small. So then you get a large negative number. Okay? If, and this is a really nice world, so if the lengths are 1, so if the lengths of the vectors are both 1, here, what's the notation for length that this book uses? This. It's also called a norm, or the magnitude. In physics, they'll call it the magnitude. So here's the norm, which is the length. And we use the Pythagorean theorem or a generalized Pythagorean theorem to find that out. So if there were two components, it would be a squared plus a 2 squared square root. So, okay, so if the lengths are 1, then the dot product will be 1 if they are perfectly related. So if they're the same or heading in the same direction. 0 if they are unrelated. And a -1 if they are opposite. If they're pointing in opposite directions. Opposite. That's supposed to be a period because I can't spell. Okay. What do we mean by unrelated? Perpendicular. Geometrically, that means they're perpendicular. If I have two vectors, no part of this vector covers this vector. You can also think about it as information. There's some information in this vector about this vector, because as I go this way, I also move along. I can get some of the place where this vector gets. Unrelated is perpendicular, not opposite. Opposite is negative related. So in this class, we have a special name for perpendicular. Orthog, G-O-N-A-L? Gosh, my spelling is so bad. Orthogonal, that's the same as perpendicular, okay? So the ortho center of a circle, I think, is where the altitudes meet, and altitudes are when you drop a line from a vertex perpendicularly to the base. So if you do that with all of them, where those meet are called the ortho center. Yes? So in this case, since they're both 1, they're the exact same vector. But yeah, right. But if they're close, I mean, if they point almost the same direction, it'll be a large number close to 1. Maybe a number close to 1. I mean, it'll be less than 1, but it'll be close to 1. So maybe large is the wrong word to use there because it's only 1, but it's all relative. I don't know if I answered your question, though. You okay? You good? Other questions so far? Yes?
So just to clarify, if two vectors are perfectly related, now you can have like two vectors that are parallel that point in the same direction, and that would be perfectly related?
Yes. Yeah, because vectors, yeah, as long as the vectors are pointing in the same direction and they're the same length, they are the same vector. So we usually when we start talking about vectors, we move them to the origin. This is called standard position. But if I have this vector and I move it over to here, as long as it goes, over the same and up the same as this one, then, in the same length, these would be the same vectors. So, yep.
Is there a benefit to having a vector in a non-standard position?
Yeah, when we start adding vectors, we will put one in non-standard position, right? If I want to see what happens if I add this vector to this vector, then one way to make sense of that is I can displace that and put it up here, and then I can start to say, oh, where am I going to end up? I'm going to end up at this position right there. So this vector is now in non-standard position.
Because we use like a shortcut to figure that out, but we don't actually put the vector.
Yeah, so this is, with this representation, this geometric representation, yeah, you can do that. But when you write down a vector, when I write down this packet of numbers 2, 5, that doesn't have a particular place yet on here. If we are going to do it, the natural place to put it is in standard position. Say, okay, I'm going to go from the origin to the point 2, 5, 2, 5. So, did that help? Okay. So to do a dot product, here's a key thing. To do a dot product, they have to have the same dimension. These A's and B's have to have the same dimension. Got another color here. So you can't do a dot product if one has a packet of 2 numbers and one's a packet of 3 numbers. Doesn't make sense. You can't do a dot product with a scalar and a vector. They're different dimensions. You can do a multiplication, you can do a product, but it's not a dot product, it's just a scalar product. So, all right. So dot products are 0 if the 2 vectors are orthogonal. This is connected to something that a lot of you already know. I know all of you have been taught it before, you just may not remember it. Suppose I have a line, y equals 5x plus 2. What is the slope of the line that is perpendicular to that line? Let me just shout it out. Negative 1/5. Okay? Y equals a negative 1/5 x. We can add anything to that. Why is this perpendicular to this? And what does that connection have to do with dot products? Let me draw out a little bit. I didn't do this really well. That's not really a slope of 5. 1, 2, 3, 4, 5, 1. See, that's 1. If this one looks bigger than this one, it's just because of the angle you're at. I drew it perfectly, but it's okay. This goes over 1 and up 5. Okay? So what vector would be associated with that slope? 1, 5. What about the perpendicular line? What does the slope minus 1/5 mean? That means I go over 5 and down 1. So because it's negative. So I can also, there's another way to think about it as I could make it negative 5 and 1, because I think I can go this way 5 and up 1. So I can go negative 5 and up 1. What's the dot product between those? 5 times 1 plus 5 times a minus 1, 0. So you guys have been actually dealing with this property for a long time. So, okay. All right, let's get a little more technical. Well, let me do A's and B's because my U's and V's look too much alike. So if you've read the peanut butter book, you would have seen this before. If you read the section, you would have seen this before. This makes this more precise. If they are unit vectors, then you get a 1 from the dot product if they're perfectly related. You get a 0 if they're unrelated, and a minus 1 if they're opposite. Well, more general than that, you get the cosine if they are 1, if they have a length of 1. But by dividing by these lengths, you create a dot product of 1. That's the same as A over A dot, B over the length of B. So this is the same as this. Using properties of the dot product and scalars, we can write this either way. But this is a unit vector. This is a unit vector. Unit just means it has a length of 1. Okay? Well, if I do some rearranging, then I get the dot product is equal to A times B. These are just numbers. These lengths are just numbers, right? There's a real number. It's a real number. Has a length of 5. Has a length of 3.2. Okay. Times. That's not dot product. There. Cosine of theta, where theta. I don't think I had enough parentheses there. I'm just kidding. All right. So theta is the angle between A and B. I need to be better at putting my arrows over. These are vectors. Okay. So if I take two vectors, no matter what the dimension is, there is an angle between those. They lie in one plane, and I can think of an angle between those. And this relationship holds. If I shrink those, scale those to have a unit length, then take the dot product will be the cosine. Or if I take the dot product of the cosine of the angle between them multiplied by their two lengths. Now the book introduces an important inequality called the Koshi-Schwartz inequality. And it says A dot B absolute value? A dot B. I can't remember. I think it's absolute value, yeah. Is always less than or equal to the product of the lengths. This is a dot product here, because this is between vectors. This is real numbers, so it's not a dot product. This is, okay, just regular real number multiplication. And if we just throw out this, you're like, what in the world? Where does that come from? But if you connect it back to this, you can reason see why. Is cosine, if it's 1, we get an equality here. What does it mean, though, with these vectors if the cosine is 1? What's theta? 0. So what does that mean about the vectors? They're the same vector. They're pointing in the same direction. And so then it's equal. But if they start to point in any other direction, the cosine will be less than 1. And the dot product will be smaller than, like this side will be, did I do this wrong? Nope, I did it right, yeah. So the dot product will always be less than or equal to this side, or the hand. Rami? Yeah, to prove this? Yeah, the law of cosines is one way to prove this. So you guys may not remember the law of cosines. If this is A and this is B and this is C in a triangle and this is angle theta, it's like a generalized Pythagorean theorem. So C squared is A squared plus B squared. That's true if this is 90 degrees, but this is true for any angle, minus 2AB times cosine of theta. Hope I did that right. You can check and see. I make mistakes all the time, so.
Might have been too long since I had a geometry class, but can you use cosine of right triangle?
No. So well, you can always make your right triangle. So yeah. So you can always make it when you need one. But cosine is based off of angles, not triangles. Although rarely have you guys seen cosine of just an angle. We almost always throw in a perpendicular there to think about right triangles. Good question. We've kind of trained you to think that way. So here, if theta is 90 degrees, then then it's 0, and you just get the Pythagorean theorem. Nice. Okay. Another inequality. The Greeks would say, if you don't know this inequality, you're dumber than a donkey. Okay? If we want to BYU, I might use another word instead of donkey, but so this is called the triangle inequality. So this is the vector A, this is the vector B, this is A plus B. So if you think of these lengths, triangle inequality says the length of A plus the length of B is always greater than or equal to the length of A plus B. Why would the Greeks say that? So Euclid, he's a Greek geometry, spent a lot of time trying to prove that. The proof is not easy. And this is why he was ridiculed, because they said, well, if you put a donkey at this end over here, you know why I'm not in the art department. It's more like a deer. If you put a deer at this end, and you put food over here, the animal's just going to go this way. It's not going to go this way. It knows it's the shortest path. So even a donkey or a deer knows that. So you can't make a triangle unless you have two sides. The sum of two sides are longer than this one. So if the sum of both of these is equal, if this is equal, that means A, you'd get to here, B, you'd go the rest of the way. You'd just be right on that line. So that's the triangle inequality. And Michelle told me yesterday, she said that's like the most important inequality that she used in one of her classes, right?
So in like upper division, like if you ever have to take theory of analysis, this is like one of the first they teach you, and they say this is by far one of the most important inequalities in mathematics, and you use it all the time. So if you ever take Math 341, triangle inequality is very important.
Okay, it's really slick that we can use dot products to find angles. Okay, so you can use dot products to find angles. I remember this problem on a state math contest, and I couldn't solve it back then. And then it came up again on a woodworking project I was doing. So we're not going to do this whole problem right now. I'm going to explain it to you. Hopefully we'll do it next week. If not, it might end up on your homework. We'll see. So if you're trying to cut sheets of wood to make a pyramid top, so there's my really bad pyramid top. Each of these has a thickness, and you want to cut the edges here. Here's a sheet, here's a sheet. You have to cut this edge to meet up the right way. And I have to take these, lay them down on my table saw and cut them. What angle do I put that table saw at? And you can use the dot product to figure this out. Let's zoom in on one of these edges. Like I've got an edge. I've got these two pieces that are going together in here somewhere. And I've got to figure out what this angle is or this angle is. And all I need to do is find two vectors in here. I do have to make sure they're all in the plane perpendicular to yeah. I do have to be a little bit careful because my table saw can only cut, how do I explain this? I do have to be a little bit careful about which vectors I pick, but I can't pick vectors, for example, if here's my cut, I can't pick vectors like this. They've got to be perpendicular to the faces of my wood. So I just have to find those two. Then once I get two vectors, I can normalize them, take the dot product, and that'll tell me the cosine of the angle. Take arc cosine. I know what the angle is, then I can set my table saw to. 1.3 is dealing a little bit more with planes and lines in space, so we'll have more tools to actually do this. All right. So in practice, dot products are used a lot in matching or ranking things. If I remember right, this is how old I am, when Google first came out, they actually used a cosine, what's called a cosine ranking. They basically used a dot product to rank pages. They don't do that now. But when you search, they actually gave a number, and I'm pretty sure the number they gave you was the cosine of that page matching to your search. So they would take your search, whatever it was, and they would turn it into a vector. I don't know how they would do that. You could imagine if you searched 5 words, they would just have each of those words, they'd make a 1 next to it. Then they'd go look at all the pages. You could easily just say, how many of this word is in that page? And they'd put it there. How many words on this page? You know, this is page 1. They just count up the number of words. I don't think this is what they did. This is a little too simplified, but just to get the idea. And then they could take your search, and they could just dot product with that, or find the cosine of the angle between those two vectors, and the ones that were closer, the ones that had the higher one, that's the the pages they would send you to first. So they would basically use a cosine ranking early on in Google. Ranking and matching, this cosine algorithm gets used a lot, which is basically just a dot product of unitary vectors. So I had a couple people. I had 4 males and 4 females. Can you go to the website? Go there. And, oh man. Yeah, go to White Harmony. So I had 4 males and 4 females, and they took a quick preference analysis. I have 9 questions on how much they like to do different things. Walking on the beach, fixing cars, reading a novel, playing Mario Kart. I can't remember what other stuff I have on there. So watching cooking shows, okay? If I'm running a match dating app, what am I going to do with this data? Who am I going to match up with? Okay, I have their information. It's easily captured as a vector, right? I've got these 9 quantities, right? These scores on what they've done. Okay, how am I going to do some matching up with people? There's 2 ways that we can do this. What time is it? 1:37. Oh man. There's 2 ways we can do this. I'm going to pretend everything's in 2 dimensions. I'm not very good. I haven't practiced my 9-dimensional drawing. Okay, so let's take here. Go to the results. Go to eHarmony right there. All right, Philly Polkenhotter. Philly? Foley. What is that? Philly. Okay, this is Philly. Philly is a male, I'm assuming. Yep, Philly's a male. Okay, so we're going to try to match Philly up with some females. This represents his vector. I can look at the other vectors of the females, and I can do there's 2 ways that I can try to see who's close. One is a projection strategy. I'm going to project each of these vectors down onto Philly's vector. And then what would I do? How would I know who I should try to match up Philly with? The one that's closest to this end. So this would be the first choice if this is how it looked like. The other strategy is to do the cosine of the angles and just pick whoever has the smallest, or whoever has the largest cosine, which corresponds to the smallest angle. Okay. I was hoping to walk through a projection, but let's do cosine and then I'll walk through the projection because I have the cosine one set up. Okay, you want to watch? Just hop out for a second. Okay. So I'm going to take Billy's data here, and I'm going to paste it in. Here, we'll paste it in right here. These were just some fake ones I was using to practice. But we're using real fake ones now. And let's check and see how chicken, okay, chicken, we'll try this. We'll see how good chicken goes. We'll see if Philly likes chicken. Okay, so what have I done here? Can you guys see that okay? There, is that better? All right. The first thing, below each of these vectors is I calculated the length. So how do you calculate the length of all these? I have to square each one. Think of the Pythagorean theorem. I have to square each one, add them together. So here I've squared each of these. Like this is just B4 squared. If we look at B4, here's B4. So 4 times 4 is 16. 2 squared is 4. So I squared them all, and then I added them up, and I took the square root. So Philly has a length of 9.3, and chicken has a length of 11. Wow. You know, chicken really likes things and hates other things. Look at that. Lots of 5s and 1s. All right. Here I calculated the dot product. So I just multiplied 4 times 5, got the 20. 2 times 1, got the 2. And then I added them all together, and that's right here, 95. Add all those up, okay? So it's positive, so that's good. But we actually have a problem with the way I set up this survey. What if someone picked 1, 1, 1, 1, 1, 1, 1, and someone picked 5, 5, 5, 5, 5, 5, 5? They shouldn't match up, because one person doesn't like any of these things, one person loves all of those things. But what happens if I take the dot product of those? If I make them unit vectors and I take the dot product? It's, yeah, they're pointing in the same direction. One's just longer than the other one, right? If you think of 1, 1 and 5, 5. So 1, 1, 5, 5. If I make them unit vectors, they're both down to about here. They look like they're the same. So let's change things, okay? Let's make, instead of a scale of 1 to 5, let's go -2 to 2. So that's what I did over here on the right. So see, lots of 2s and -2s because the chicken loves it or hates it, okay? And Philly, yeah, it's kind of in the middle of lots of things. Calculated the lengths down here, so there's the lengths. And did the dot product, and I get a dot product of 8. And if I divide by both lengths, I get 0.617. Okay, so the cosine of 0.617, that's less than 45 degrees. 45 degrees is the cosine of 0.7, right around 0.7. Okay, chicken, well, but it's positive at least. So potential, Philly has, you know, Philly and chicken. There's potential there. But let's see, let's pick another female, see if there's a better match. Balthasar, okay? I'm sorry, Balthasar, if I massacred your name, okay? Let's see who is a better fit here. Paste it, transpose it. 0.4, even worse. Right now, chicken's in the running. Okay, still in the running, okay? Oops. Steve Jobs. Mary. I'll do. Let's marry me if male or a female. Okay. So why did I call this Y harmony? Yeah. Like there was an old website called eHarmony. Some of you may have heard the commercials. Way before the swiping. And this, I'm sure this is what they did. They'd make a big profile, and this was I'm sure a major part of how they would match people up. So Brook Hall, 0.45. Still, chicken's the best match so far. So you get the idea. So so the dot product tells you how similar two matrices, two vectors are, two packets of numbers are. We can use it to calculate the cosine. We can use it to do projections. I'm not going to have time to walk through one. I happily will, because I know some of you will want to leave. And I will walk through a projection on how to do that projection. We also talked about two inequalities, the Koshi-Schwartz inequality and the triangle inequality. So any questions from what we've talked about today? Oh, yeah, so Okay, so right, I have this cosine here. The dot product, if they're unit vectors, so I divided by their length. So this is the vector of the unit. Yeah, they're unit vectors. They're going to be perfect if this is what happens. That can't happen. They're going to be the same length. If they're both like this, I'm going to get a 1. Okay. If it's like this, one's like this and one's like this, I'm going to get a 0. If one's like this, I'm going to get a -1. Okay. 45 degrees. It's 0.7 about. It's a square root of 2 over 2. Negative 0.7. So we got a negative 0.45. It's going to be something like this. Because if these are both unit length, and I do a projection down here, and if this length is the cosine. So 0.45, or that length is the product. 0.45. That length is the dot product between them. So if things are more similar, you're going to have a larger positive number. If they're unit vectors, then the highest you can get is 1. If there's some negative relationship where they're actually pointing in opposite directions somewhat, then they start to become negative up to a -1. Okay, that make sense? You're welcome. Thanks for asking the question. Other questions? Yes.
So is there such a thing as like dot product, like same dimensional?
There is a matrix multiplication that we will get to. It's not the same. No, they are related in that you can write a dot product as a matrix multiplication, but you have to do one vector like this and write one vector like this, and then if you do this as matrix multiplication, then you get the dot product. So we will do that. All right, I'll make a video about that where I walk through a projection example, and we'll post it online. So, yeah. Have a great day, you guys. Philly, I'm sorry we couldn't get you a really good match. Oops. Yeah.
There's a website that I used a while back that was like, find out which political candidate matches your views. They give you a series of questions like that. In addition to each policy question, it also said, how important is this issue to you? So like it would also take that into account. How would you apply that? Would it be a coefficient on each of the components?
That's right. Okay. Yeah. So you basically each of the questions would be a dimension, and then that would be your magnitude in that direction. So that makes sense.
Yeah.
And that's how I assume they would.
It seems like that might be it, but yeah. So.
Yeah. I mean, there are a lot more advanced tools now that people use, but yeah, this is a basis for a lot of that.
Okay.
That stuff
I really appreciate that explanation because I've heard tried to understand dot products before, but this is like huge and helping me.
Well, thanks.
Get to the next level. So thank you.
You're welcome. Braden.
Yes.
I have a nephew, Braden. That's how I made the connection. And with the last time I got your name last time, I was like, oh, I just have to think my nephew. Okay, go ahead.
So I've always been someone who like really learns well listening and then using the textbook to help me afterwards, fill in gaps or answer questions. So I was just wondering if you had any recommendations for helping with this, because it's kind of flip-flop now, and now it's like learn from the textbook.
It is. Well, so that's one reason why we do the videos, because we haven't expected students in general in math class to learn much from the textbook, but everyone in this major is going into technical careers, and you're going to be expected to read technical material and learn from it. So you may as well start now. So that's one of the reasons I do it. But yeah, one of the reasons we do the videos with some explanations is to help and support that. So, and
So the videos that we'll be having are kind of like helping to explain the.
right, yeah, they usually will do a brief explanation of the main concepts and then walk you through some problems. And then hopefully that'll help to support as you go through and read the textbook. So, and the idea is not that you know everything perfectly, just, you know, from those experiences, but hopefully you have questions that you understand, like, hey, or you know what you don't understand, and then you can be asking questions in class and looking for those things in class. So, that help?
Yeah, I was just trying to figure out how to be learn most effective. Yeah, thanks.
Yeah, you're welcome. Okay, remind me your name.
Elliot,
Elliot, dang it, okay.
will you be going over those like test problems ever?
Oh yeah, I can share the solutions to those. Can you send me an email?
Yeah.
Could you do that so I don't forget?
Yep, will
Yes.
do. 'Cause I was looking over them. I really don't know how to do them, but I was giving them
Yeah.
a shot.
Okay, perfect, perfect. Okay. What's your name? Molly. Oh, you're the brand new Molly. Okay, great.
My question is on the textbook. Is that it's all online, right? And
Yep.
the BYU bookstore will charge you $70 for those online classes. So do I need to opt out of that, or do I need to keep that?
If you're registered for this course,
Yeah.
then, so, well, tell me what you've done with the bookstore. You shouldn't have anything to do with the
Oh,
bookstore.
it's just on my book list, and it says
Oh.
if I don't opt out by the add drop deadline, then it's going to charge $70 to my account.
Yeah, so you don't want to opt out.
Okay,
You want to
so
keep
I do
in.
want that.
Yep,
Okay, just wanted to check.
yep. That's great. I'm glad you asked. Okay. Can you go to that website? There is a tinyurl.com yharmony. There's a short survey. Okay, can you fill that out? You don't have to use your real name, and you don't have to fill it out. You don't have to be true to those things. Can you also do that? Remind me your name. Tanner. Dang it. Yeah, they were capitalized. So, okay.
I'm over it though.
Oh, flibs. Ian. Did you see here last time?
Yeah, right here.
What does it start with?
C.
Chris? Dang it.
CO.
Colton. Coulter. I'm just kidding. What is it?
It's Connor.
Connor. Dang it. Sorry, Connor.
That's all right. I figured out what my question was now.
Oh, perfect.
Really. So, I had a question about the proof questions on this is so funny, on the online.
Yeah, the
on
book homework.
textbook homework.
Mm-hmm.
Do you have a class starting in 5 minutes?
I do have a class. So if you're around an hour, I can help you, or if you just email me, and then we can set up a time, or I can just make a video to answer your question or something like that. So.
I've been told how to get help from TA so many times that I don't know where to go to get help from TA. So I feel like
Yeah, so go to the.
But it's only been like 1 or 2 classes in.
Okay. So Ian and Connor, can you do me a favor and go to that website and fill out it's just a quick 11-question survey.
Okay.
Don't use your real names. You don't have to pick the preferences as if they're you. Okay? That's what it sounds like. I can see why it would sound that way. So I'm actually teaching about dot products today. And oh, good. Good. I'm glad you see the connection, Tanner. Molly, you will see the connection too.
So we figured out how we want to do this. What we'll do is just have Zoom going on here and then give remote control of this computer to my laptop or her laptop if she's not here. And so if she's here the class before, she can just handle that. But if she's not here or whatever, then you might have to do it. Here's how it works. So you just do share screen, and then you have the whole screen shared. And then you click remote control, give it to quarterback.
Oh,
And
wow.
then probably what I'll have, are you using these through the whole class? Because the tricky thing was we were trying to figure out how to show the PowerPoint and the whiteboard, because sometimes you're using both. If we do it like this, then I can see the PowerPoint, see the whiteboard, and control the camera all from my computer.
Oh,
And it doesn't have that timeout. Like this code to use this website is a problem. But if I'm remote controlling this computer, then it works fine.
Gotcha. I'm not going to, so these won't be up the whole time, but sometimes I'm going to have, if I'm using the computer, then it's not a big deal. Because when I go to start using the spreadsheet
Do you ever
stuff.
add the whiteboard and wanting these slides to be up? It's fine if you
I don't know.
And you'd be able to see what I'm doing. Like whatever you're seeing on here is what they're seeing on the Zoom call. You could also just like tell me, it's like a hey Corey, you can get rid of the PowerPoint, like leave the PowerPoint for here.
Yeah. I don't know. I'll have to think. What I'm teaching, I'm going to be in the moment, and I'm not even going to be thinking about stuff like that. So.
I'm going to try like doing this class from back there as if I was remote.
Okay. Then we'll see how it goes.
Maybe I'll be staying.
Yeah. See, like already right now, it seems like that's going to be too small for them to see.
Yeah. So if it needs a time when you just need the PowerPoint, and you can just make it full screen, and that's fine because that's all they need to see on the Zoom call at that moment. What's tricky is, like I think no matter what, even if I'm sitting right here at this table, I don't use a way to show the PowerPoint on the camera and show the whiteboard.
Right. Yeah, but so. Right, but if you've got presets, well, then you just keep switching back to that screen and this screen with the presets, and then that's maybe not ideal, but that's something we can do. I think that's what the people who set it up would have, envisioned you would do. So, okay, you still want this shared? Okay. Okay.
You can feel free to like. Even if I'm controlling it at the moment, you can just come over and have a PowerPoint on the computer if you need. Because if you want to show the PowerPoint in that page, you see the Zoom call.
Right. Okay. All right. Okay, we'll see how this goes. Again, turn up the audio. Connor, Ian, can't remember. I forgot everyone's. Trevor. Brendan, man, I think I fried my brain trying to learn everybody's last time. So, dang, this is like so bad. Trevor, thanks for sitting in the same spot. I just knew there was a Trevor there last time. So, that's how I learn these things. So, it was really, after I finished this class last time, I felt like I couldn't remember anyone from the first class because I had to remember 2 names for every spot and getting them all mixed up. But Delbert, see, I got Delbert. He was in my class last time. So Molly, she's a new student. Oh, dang it. So bad. Henry, remember that? Dang. Just assume I don't know your name, I guess. I worked so hard. All right, is it time to get started? Let's get started. Who'd like to start us off with a prayer today? What brave soul is there? Thank you. See, you wore a suit, just to say the prayer.
Our Father in heaven, we're so grateful that we have the chance to meet together. We're so grateful for the opportunity to learn of the workings of thy creation. be safe and productive during this uncertain time. We ask for these things in the name of thy Son, Jesus Christ.
Amen. All right. Before we dive into some linear algebra, a few things. I wrote the homework that's assigned today up here. So usually you won't have this much. But we're in the transition phase where we're going from doing the homework after class to doing the homework, some homework before class. So it's kind of doubled up between now and next Thursday. Luckily, like section 2.1, so we'll cover 1.3 and 2.1. They're really small. 2.1, you guys are going to, some of you are going to think is a joke because it's like so simple, stuff you learned 5 years ago, okay, about solving systems of linear equations, okay, elimination, substitution sort of stuff. You're going to be really comfortable with it, luckily. After that, things will settle down and you'll have, between two classes, you'll finish up stuff with book homework on one class, and you'll start doing prep through the online homework and the reading and the videos for the next class, okay? So there is no online 1.3. There's an online homework 2.1, and it might even be just 2.1a, but you'll see on there. Read these sections. Online homework 2.1. On this online homework, it'll ask, did you read the section or sections? I can't remember that we ask if you read 1.3 on there. And did you watch the videos? So you can get your credit for doing that on the online homework. And then the book homework, we're going to finish 1.2 today. You can get on and do the book homework. Book homework, we're still in the middle of trying to set up grade scope. So your book homework will be uploaded to a program, so we don't have physical papers passed around. After Thanksgiving break anyway, you won't be around to hand in physical papers, or the TAs won't be around to pick them up. The other teachers, almost all of them use the same set of slides, and so during lecture, they just walk through those slides. I have those slides. I'm making them available to you guys. We're going to put them on Learning Suite. I'll show you where they are. If instead of watching the videos, you want to just study the slides before coming to class, that's also just fine. And then when you get the question on the online homework that said, did you watch the video? If you studied the slides, you can say yes, and you're not lying, okay? All right. Any questions about this? Okay. Any questions from the syllabus? No. Okay. Let me just walk through a few things so you make sure you know where things are. This is the Cengage WebAssign website. When we talk about online homework, this is what we're talking about. I can click on section 2.1, and it brings up the problems, and I can work through and do them. Okay. The ebook is right down here to the right. So if you want to see the version of the ebook, you come down here and you click on linear algebra, and it pulls it up in a new window. And the book work. Where did my Learning Suite page go? One of these? Anyone know how to move this thing? Aha, there. Okay. Okay, what was your question?
On the online homework, there was one question I asked about components of one vector, and I couldn't figure out the format of how it wanted it to go in. For example, x space comma space y. Is that how it needs to be put in? I couldn't figure out. It never accepted any answer.
I don't know. Can you look at what number it is, and then send me an email, and then I can research that. Okay. Right. That is one of the frustrating things about all online homework systems is you have to do them in a certain format.
Right.
So one of the nice things about online homework systems, though most of them, and I think it's true with this one, is it will do a bunch of simplification for you. Like in problems where you have a big algebraic expression, you don't have to do the simplification, you just put the whole thing in there and it will do, and it understands if it's equal or not. So it can save you some work that way. Yes? No spaces. Yep. No, we're anti-space. Okay. We're all up, we're just a point. Okay. Just kidding.
Also, I noticed if you feel like cosine of something, don't simplify, just leave it as like cosine of that thing. Don't have to solve cosine of like.
Oh. Don't end up being like, don't write 1/2 if it's cosine of. Gotcha. Okay.
I did spaces and I got it right, so I think it just ignores spaces.
All right. Okay. We're as close as we get to a political debate in mathematics. Just kidding. Okay. There was a question back here. Your spaces worked? Okay. There's another. Wow. Okay. This is another reason why you don't have to get 100% to get 100%. So you just have to get 85% of the points. So when you have things like that, I can tell you stories about other homework systems we've used in the past that have been so frustrating to use and crazy hard, but now's not the time. Okay. On Learning Suite, if you go to like section 1.2, if you click on this here, it shows you the problems to do in the book. So then you can go back to the WebAssign page, click on the book, and then go find where is the, oh, just, yeah, skip. And then you go to section 2.1, and then you can read whatever section, go find the problems at the end. Okay? Got a PhD, I can't run a mouse. Okay. I didn't get enough master's degrees, I guess. Should have done a postdoc. So you can also get those if you go to assignments, and then you click on any of these, then it brings that up, brings it up also. So under the content page, so we've updated this. So the videos that you're asked to watch before class, they're right here under videos. One of the TAs is putting the slides. She's trying to, the slides come in big files. She's trying to chop them up so that you have everything just for 1.1, everything for each section, and she's going to put it in these sections here. Yes. Yeah, we're trying to set up a program called GradeScope, where yeah, you will do exactly that. We're still in the process. As soon as we get it set up, we'll let you know how to do that. Thanks for asking that question. This is an example of those slides that the other professors use. So has some worked out examples. They hit a lot of the most important things from each of the sections. So they're boring, but you know, doesn't mean that they're not important. It's just boring. Okay. We're trying to get all the lecture slides right here if you want them, but you shouldn't have to go to that side. The peanut butter book, it's right there. I did fix the problems on the last page, and I put page numbers on. And Zoom link. This is one place to find out where all of the office hours are for the TAs for this class, and my office hours and the Zoom links. So put that all in one spot. Okay. So any questions about anything like this? Running the course, complaining. You want to drop code? Just kidding, you don't need to drop code to drop the class. So, okay. Make sure I didn't miss anything. It can get cold in this room, so you might want to bring a jacket. We do have 2 kids between this class and the last class. We have 2 kids that are in quarantine because they've come into direct contact with someone that has COVID. One of them has a roommate that does have COVID-19. Please be careful. Okay, we are Zooming. We are recording these, and we have the Zoom set up so they can zoom in. If we have Zoom problems, so this might happen to you. This might happen to all of us. We might all be on Zoom later this semester, who knows? But or I might be creating videos and just showing them online. Depends on how it goes. But be safe. We already have people that can't be here because of COVID. Dot products. Okay. When you're dealing with packets or vectors, one natural question is how similar or different are these two packets, or these two vectors? The dot product helps us to answer that question. The dot product takes in two vectors and it spits out a number. Number meaning a scalar, a real number, a scalar. Scalar. We write it A dot with a big dot B, okay, where these are vectors. And the procedure for doing that is you multiply the corresponding components. And you just add them all up, okay? So you just get a number. A dot product is a number. It's a number that helps us know how similar or different they are. Key thing, these must have the same dimension. They've got to be the same length. Okay, length means different things. I mean, they've got to have the same number of quantities in the packet. So length here in terms of 3 or 3. You can't take this and dot it with this. Okay, just makes no sense. It's not defined. Okay. And they have to be packets. I mean, they have to be vectors. If you have a scalar, you can multiply a scalar times a vector. That's okay. But it's not a dot product. So if you have a scalar dot a vector like this, you did something wrong. Like that's not right. You can multiply a scalar times a vector, but that's scalar multiplication. It's not a dot product. Okay. So. Okay. All right. So if the products are similar, if the vectors are similar, the dot products are going to give you the dot product is going to give you a large positive number. If they're unrelated, then it gives you 0. And if they're negatively related, how do you spell that? Then you get a large negative number. Okay, large is relative. It depends on the lengths. Exactly how large depends on the lengths of the vectors. Since that's sometimes not a good thing, dot products are really nice if the two vectors have a unit length. So if they have a length of 1. So if they have a length of 1, if A and B both have a length of 1, then if they're similar, they will be large which is close to 1. If they're the same, they will be 1. Okay? They're pointing in the same direction, the dot product, and they are unit length, it will be 1. If they're unrelated, it'll be 0. If they're dissimilar or negatively related, it'll be a, I don't know if I should say large if it's less than 1, but close to a -1. And if they're opposite, remember how to spell opposite, then it will be equal to a -1. So this tells you a measure. If they're of unit length, this is a really nice way to talk about how close they are, how closely related they are. In fact, it's more technical than that. If you've read the peanut butter book, you already know this, but A divided by the length of A I'm not offended at all if you just yell, hey, can you write bigger? Because I slowly start writing smaller, and then I remember. So, okay, I'm not used to teaching in a class this size. Dot B. Okay, so these double lines on each side. Let's just talk about those really fast. That's the notation for the length of B. Okay? You know, like if you were to go from the head to the tail and measure it out on the grid or in space or whatever, that's going to be the length. We use the Pythagorean theorem or generalized Pythagorean theorem to figure that out. This is if we just had two components in B, this is what it would be. If you got more components, you just continue the same pattern. You square them all and add them up and then take the square root. Sometimes we'll call this a norm. So the norm just means the length. Physics, they call it the magnitude. Some other books and some other classes, they will just use one line. Okay, absolute value, because absolute value is the length of a real number, like the distance from 0. So they use that same thing. And this book that we use uses doubles. Okay? So if I take a unit vector, A, it has a length, this has a length of 1 because I've divided it by its length. This has a length of 1, I've divided it by its length. That equals the cosine of theta, where theta is, it's the angle. What was that? Yeah, this is the dot product. So is the angle between vector A, vectors A and B. So if you're in 2 dimensions, right, you can draw it out. If you're in 3 dimensions, if I take 2 lines, no matter how they are, I can, I can orient these in space. They're still in the same plane. I can still think about an angle. And we generalize that to hyperplanes. It could be 9, 27 dimensions. It still works. Yes? Yep. Okay. Great question. How about I'll make a video and I'll post it so everyone has that. I would love, if we had time, I would actually love to derive this. I did it to make sure I understood it a couple days ago. So yeah, it's not that hard, but yeah, I'll go ahead and do that. Okay. Great question. It does come from the law of cosines. Some of you may not have remembered the law of cosines. When I was in your shoes, I couldn't have told you what the law of cosines was. It's a generalized Pythagorean theorem. So if this is side A and this is side B and this is side C, and this angle is theta, then C squared equals A squared plus B squared. That's only true if theta is 90 degrees, But if you subtract this piece off, then that relationship holds for any A, B, theta, and C. So, and yeah, you end up having to write each of these lengths as vectors and stuff like that. So, okay. All right. Any other questions so far? I know I'm just as boring as those slides that I was talking about. Okay, we have a, what do I mean by unrelated here? When I say two vectors are unrelated, it's kind of a weird thing to say. What we mean geometrically is they're perpendicular. And we have a special name for perpendicular in this class. Orthogonal. Okay, orthogonal means perpendicular. One reason that we use a different word than perpendicular is it allows us to talk about things that don't seem, where it doesn't make sense to say perpendicular, like sine waves and cosine waves. They're orthogonal. We'll say they're orthogonal, but it's hard to say, like, why would they be perpendicular to each other? But there are reasons, when we get further on, there are reasons to see, like, oh yeah, they are orthogonal. But so we have a new word. Mathematicians love to come up with new words. So orthogonal, that means perpendicular. This idea that the dot product gets you 0 if things are perpendicular or if things are unrelated, you guys have actually already been working with that idea. It's just been hidden. So if I take y equals 2x plus 1, your college algebra or pre-calc teacher may have said something like, find an equation of a line whose slope is perpendicular to that line. What slope, what would the equation line have to be perpendicular to this? -1/2. Okay. Well, how are these things related? Well, if the slope of 2 means as x increases by 1, I go up 2. Over 1, up 2. Okay, 1, 2. That's really, sorry, I should have drawn that bigger. What does the slope of a -1/2 mean? Plus something. That means I go over, how far in the x direction? Over 2, down 1. Or I can think of going over -2 and up 1. So either one of those is fine. So if I think of this movement that happens along this line as a vector, what vector do I get? 1, 2. 1 in the x direction, 2 in the y direction. If I think of this movement that happens with this line, what happens? What vector do I get? -2, 1, or 2, -1, doesn't matter which one I do. Well, what happens when I take the dot product of those? Zero. So this, you can think of this as 2 over 1, 2 in one direction, 1 in another one, -1, 2, -1 in one direction, 2 in another direction. The dot product of those is 0. So, okay. What's next? Okay, it might be time to wake up your neighbor. It's about time that they're nodding off. So make sure they're not drooling on their notebook or something, or on their phone. Okay. I rearrange this equation, okay, this is the dot product up here. These are just numbers, so this is just real number multiplication down here. If I rearrange this, I get A dot B equals A B times cosine of theta. Okay, this is a dot. These are just real numbers. If A equals B, or if they're pointing in the same direction, what's cosine? Think of the cosine. Here's the cosine curve. So if they're pointing in the same direction, the angle is 0. So the cosine would be 1. So if they're pointing in the same direction, then this is 1. And then we could just say, hey, the dot of A and B is the same as the product of their lengths. But what if they're not pointing in exactly the same direction? Which side will be larger? The left will be larger, okay? So if I keep this, if I just eliminate cosine, which side will be larger? If I just drop this, I'm going to have an inequality. I'm going to have an inequality. Which way should the inequality go? You know, it could possibly be equal. It should be less than or equal, or right greater than or equal. It's going to be less than, because this will sometimes shrink this side. If I always keep this side as large as possible, which is when cosine is 1. Okay, I do have to be careful. I do have to adjust my signs. So, well, it still should be okay. But this will always be larger than the dot product, and they will be equal if A and B are pointing in the same direction, exactly the same direction. This is called the Koshi-Schwartz inequality. Koshi-Schwartz. So S-C-H-W-A-R-Z, Koshi is C-A-U-C-H-Y. Okay, I wish there was a better geometric interpretation of this inequality. I haven't been able to find a really good one. Okay, there's another important inequality we'll talk about. It's really straightforward. In fact, the Greeks would say it doesn't need to be proven because even a donkey knows it's true. So they wouldn't call you a donkey. They'd call you some other mean name. We wouldn't say it at BYU. So. Okay, so this is called the triangle inequality. So these inequalities we end up using to prove things about vectors sometimes. To prove that, actually, you can use Koshi-Schwartz. So the triangle inequality is that absolute value, the length of A plus the length of B is going to be greater than or equal to the length of A plus B. So it seems obvious that this length is shorter than this length. But you'd have to be careful to say, well, it just seems obvious, because there's actually lots of times in the history of mathematics where people just thought it was obvious, and it turns out that they were wrong. So, but this is the proof that the local Greeks would tell Euclid. If you put a donkey, if you put a deer at this end, and you put the food over here, even the donkey knows to go that way to get to the food. The donkey's not going to go around. So even a donkey knows that. Why do you even have to prove it? Okay, so this is the triangle inequality. So we can also rearrange, well, we can also use this or go one step further to get an equation that'll tell us the angle between two vectors, not just the cosine, but the angle. So if you take the inverse cosine of both sides, sometimes called arc cosine, arc cosine of A dot B, B, that equals theta. And I'll tell you one place where I bumped into this. Are any of you into woodworking? Anyone? Oh, a couple people. Good. So if you want to make a triangle top with wood, not a triangle, a pyramid top, you end up having to find a really difficult angle to cut the pieces right on your table saw. And that angle is, you've got the face here, you've got the face here, you've got to cut that angle so that they will meet, right? You want to have, those pieces are going to be looking like this so that you can fold them together and they'll make the exact angle that you need. So it's like that. And that's actually not, geometrically, it's not an easy angle to find. But if you're able to just write down two vectors, maybe this vector and this vector, if you're just able to write two vectors down, then you can easily find it with that formula. Okay. After 1.3, where we talk a little bit more about planes and lines in space, then we can actually do this problem. And I feel like I need a 3D printed model to actually explain why this is so hard. Like, isn't that easy? It's actually not so simple. I've seen this problem on a state math contest before, like in high school. So I couldn't solve it back then. So some of you may know other ways how to solve this problem. But, yeah, so we can find angles with dot products. In practice, one of the applications where it gets used the most is in trying to match things up or to seeing how similar things are. Like, I've got some people rating movies, and Netflix knows how you've rated movies. How are they going to decide what they're going to push to you next to try to keep you watching? Okay, they would use algorithms kind of like this, because the ratings that you've given on different movies and the ratings that other people have given on those same movies, they can use those to see how similar you are to those, and then they'll push other things that the first people have liked. PageRank algorithms. The very first Google algorithms were based off of what's called the cosine rank algorithm, where they would take they would turn your search into a vector. I don't know how they do this, and I'm sure it was more complicated than this, but it's the basic idea. They would, how long is the longest snake in the world? Okay, longest snake in the world, okay? So they might just make a vector with these words. You used all these once. You could go look at pages out there and just start counting up how many words each of them used, of these words, and you could put it in there, right? And put them in there. And then what do? You use this equation to find the cosine of those two things. And if I remember correctly, in the early days of Google, they would actually show you the cosine. Underneath each page rank, they would show you a number. It was a decimal number, and I'm sure it was the cosine of those two, of vectors, however they created it. I tried to find images. I couldn't find an image where it actually showed that, but I'm pretty sure You guys are way too young. It's like before you guys were born. Maybe, but. All right. So I asked a few people to go to this website. Here's a little bit of a survey. So I asked Molly. She went there to fill it up. And I asked a couple other guys to do it. And it's a little preference survey. So here, I wrote down a fake name, and they just rated on a scale from 1 to 5 how much they liked doing things like this. Watching cooking shows, reading novels, discussing politics, etc. And after you did this, what did you ask me, Molly? Was I setting up a dating site for a class? I could, because we can use the cosine. We can use the cosine ranking algorithm to see who is a good match to, not to Molly, but to, Molly made it, this is just an avatar that Molly made up, right? It's not really Molly. So where are we going to, so she filled it out and some other guys did. And what's your name? Ruggles, right there. Okay, so Ruggles, we'll see who Ruggles' avatar might match up well with. So, I mean, Ruggles, Molly's avatar. Cut, copy, and okay, so I already set this up so we could do some math with it. So, so let's get rid of Brooke. That was from another class. Oh, I just want to delete it. There we go. Okay, so Connor, who is your avatar? Oh, you did it as a female. We better pick a male. Ian, did you do a male? Jeffrey. All right. Okay. So let's see how well Jeffrey matches up with Ruggles. Ruggles? Ruggles. Ruggles. Okay. See if Jeffrey wants a dog. Okay, so let me explain what I have going on here. So these are their scores on a scale from 1 to 5 of how much they like to do these things. Boy, they both like to do a lot of these things, but Jeffrey not so much on fixing cars and discussing politics. Okay. Ruggles, he likes to fix cars fairly well. Maybe he thought I said chase cars instead of fixing cars. All right. So I'm going to make it so we can easily compare across people, we're going to find the cosine between Ruggles and different potential people. So to do that, I have to first find the length. So that's what I did down here. So to find the length of this, I have to square each of those numbers, add them up, and take the square root. So you can see down here, the first two numbers here were 4, 4, 5. So first three numbers, 16, 16, 25. So I square all those numbers, add them up, and I took the square root. I get 12.32. So that's the length right here. And Jeffrey, I square all those numbers. You can see it's all 25s or 1s. He either loves it or he hates it. Gets 13. And I take the dot product. So the dot product of those two is I just multiply 4 times 5, and I get 20. Right? Multiply 4 times 1, I get 4. 5 times 5, get 25. Then I have to add up all of those. This is the sum of all of those. Okay? So it seems large and positive. Okay? But large and positive is not really standardized because depending on the length of the vector, you could get a larger number, even though they might not be, even though the angle might not be as close. So we divide by the lengths. So I divide by both of those lengths, take that number, divide by both of the lengths, and I get nearly a perfect fit, 0.95. That's really good. The matches we made in the last class, I mean, the closest one we had was like 0.6. So you're going to love this dog, Jeffrey. But there is a problem, actually. There is a problem because what if someone wrote down 1, 1, 1, 1, 1, 1, 1, and someone else did 5, 5, 5, 5, 5, 5, 5, and we found the cosine between those two angles? Let's just think if we only had two variables, and someone wrote down 1, 1, and someone else did 5, 5. The vectors look like this, right? And they would come out as a perfect match, when really they should be opposites, right? Really they should be opposites, because really the center should be here, and we should have that going this way and this going this way. So we should change the scale to make sure that we're not getting a higher level of agreement than we really are. So that's what we did over here. So here I subtracted 2 from all of their scores. So now if you did a 3 in the middle, it's a 0. And -1 and -2s are things you don't like. We do the same thing. We find the length. And found the length, found the dot product, took the dot product divided by the length, and I get 0.727. So still pretty high, but not as high. Some of that was artificial. Okay, but is there a better match for Ruggles? Ruggles. Ruggles. Is there a better match for Ruggles? Connor, who was your, oh, you already did Avatar. Who else did one of these? Tanner. Balthazar Corosis, all right. Is your dog a pit bull? Because that sounds like a kind of dog that, it's a retriever chow, okay. So, paste it in, and here we go. Oh, wow. So what does that mean? It's almost 0. The cosine is almost 0, so what does that mean? Yeah, they're almost opposite. So let's look and see that, oh, some of that doesn't look right. Oh yeah, so here, not alike, neutral, not alike, neutral. Look at those, those are opposite. These opposite, not alike, neutral. Okay, there are some positive things up here, but in a lot of these they're opposite. So it's not, because it's not exactly opposite. But I don't think Balthazar, I don't think Ruggles is the dog for you. So. Oh yeah, Balthazar the cat. Well, that makes a lot of sense. Makes a lot of sense. Okay. All right. So can you see how the dot product can be used to talk about how similar things are, how similar vectors are, right? How you could rank things. Okay. Any questions about this? I am sure this is a key part of yeah, dating sites. So yeah, there's more. This would have been cutting edge 25 years ago, right? Have any of you heard of eHarmony? Like the dating? Yeah, so that's why I called it Y-Harmony. I'm sure that was a big part of them. But now with the swiping and the pictures, I'm sure they have AI stuff that also does things a lot better. Yeah? Oh, yeah. You know, I have had, this is my 15th year, I've probably had 5 or 6 people get married who met in my math classes. So 5 or 6 couples, yeah. So even a year ago, that semester, I had a large section of 113, and they got engaged that semester. They'd met each other in that class. Okay, one more thing before I turn you loose. There is something else we can do. There's another strategy we can do to see who is close to Ruggles. And instead of just looking at this angle here, you can do a projection. This is one thing I'm not going to have time to walk through. I'll make a video of walking through a projection problem so you understand how to do that. But if we have lots of competitors, okay, then one thing you can do is, here maybe I'll make a one. So this is Ruggles. Is you you can project one vector onto Ruggles' vector. Oh, I did the wrong one. That's Ruggles. Okay. You can project here, and you kind of see like how much of this person is captured in Ruggles. So that's kind of one way to see it. And then how would you rank these? Who would you pick as the first person? Yeah, the one that's closest to this point. You could have one that went further. That's why I wanted to do that. But you still could have one out here, and the projection would come down to there. Okay, and then you can say, well, who seems to be the closest on this line, and then you can go from there. So there's another strategy in matching it up, you might get some results. You could get some different results because here this is you could have this is a larger angle. This is a larger angle, but if I went out farther, then I could get closer to people than people who were a smaller angle. So anyway, so projections is another use that we use dot products for. But I'll make a video. We'll post it so you guys can see an example. All right. Any questions? All right. Have a great day. 1.2. So this is 1.2.